want you to just picture a scenario for a second.
Yeah.
It's a Tuesday. You're driving to a meeting, maybe in a part of town you've never been to.
Yep.
And you are relying completely on that little blue line on your screen to tell you where to go. Or, hey, maybe you're a captain on a ship, miles offshore, in thick fog, just trusting a digital chart to keep you safe.
We do that every single day, don't we? We've sort of outsourced our sense of direction to the sky.
Exactly. But then in this scenario, it all goes dark. The blue line just vanishes. The signal drops. The satellites, they just stop talking.
No GPS, no timing signal for the power grid,
That's
nothing.
terrifying.
It sounds like the opening of a disaster movie.
Yeah.
But based on the documents we're looking at today, that's a very real vulnerability in how we've built the modern world. We just assume that signal from space is, eternal, but it's actually pretty fragile.
And that is the hook for today's deep dive. But don't worry, we're not just here to spread doom and gloom. We're here to look at a proposed solution. We have this huge stack of documents from a company called Tedford Enterprises. There's a disclosure framework, a technical manual on something they call a node, and this really dense, fascinating letter to a scientist named Dr. Eva Marie Müller-Stuhler.
That letter is the heavy lifter here. It's basically a full-on defense of the physics behind a new concept they call the living ground mesh.
The living ground mesh. It sounds almost organic, doesn't it?
In a way it is, or at least it's designed to be. Instead of thinking about infrastructure as just dead concrete and dumb cables, they're talking about a kind of security blanket for the planet, a system that keeps everything running even if the sky goes dark.
Okay, but here's the challenge, and this is our mission for this deep dive. These documents are, well, they're dense. They're written for physicists, for engineers. I mean, the letter to Dr. Eva is just full of wave propagation theories and stuff I can't even pronounce.
It is not light reading. It's meant to convince a skeptic who has a PhD.
Right, so we're going to take this high-level engineering, this stuff written for Dr. Eva, and we're going to translate it. We're going to use what I call the third grade rule.
Okay, I like this.
If we can't explain the core idea to a bright third grader, then we haven't really understood it ourselves.
I love that challenge. Complexity can sometimes hide a lack of understanding. So, yeah, let's strip it back.
So, start us off. The problem. Why do we even need a living ground mesh? What's actually wrong with the satellites we already have?
The documents use this really powerful analogy, the glass house. Think of our whole civilization as this huge house where all the light comes from one single giant light bulb hanging in the sky.
And that's our GPS and satellite network.
Exactly. It's a total marvel of engineering when it works. But it is centralized. If that one bulb breaks because of a solar flare, a cyber attack, whatever, the whole house goes dark instantly.
And everyone's just bumping into the furniture.
Right. But there's another layer to the problem, and this is in the disclosure framework. It's not just about the bulb breaking. It's about where the light even reaches in the first place.
The inequality angle.
Yeah, the humanitarian argument. Right now, if you're in, say, New York or London, you're bathed in light. You have amazing connectivity. But if you're in a remote village or a dense jungle or out in the middle of the ocean, you're often already in the dark.
The signal's weak. Or just not there.
Exactly. And the source material argues that safety shouldn't be a luxury item. I think the phrase they use is planetary benefit. The goal isn't just faster downloads for city coffee shops. It's giving a fisherman in a tiny boat the same navigation safety as a supertanker.
So democratizing that safety layer for the whole planet.
That's the idea. So you have the fragile sky bulb and you have the unequal light. And that's where the living ground mesh comes in.
Okay, let's apply our third grade rule here. The docs talk about densely distributed ground nodes. What does that actually look like?
Imagine a spider web.
A spider web, okay.
A spider web is a mesh, right? If you cut one single string of that web, does the whole thing just fall apart?
No. The tension shifts. The spider just, walks around the hole.
Precisely. The living ground mesh is a digital spider web covering the Earth. It's made of these nodes, and we'll get to what those are in a second. But the core idea is decentralization. If one node breaks or loses power, the rest of the web just takes over. It heals itself.
That is a huge shift from the one big light bulb model.
It's the difference between a chain, which fails if one link breaks, and a piece of fabric, which holds together even with a tear in it.
And there was a specific detail I saw in the technical manual about centimeter awareness. Why does that matter so much? I mean, my phone knows where I am within a few feet. Isn't that good enough?
For finding a pizza place, sure. For a drone landing on a balcony in high winds or a self-driving car in a blizzard, absolutely not. Meters aren't good enough. You need centimeters.
So instead of asking the satellite, where am I? The ground itself is telling you, you are right here.
And you are 3 inches from the curb. It's a whole different level of precision.
Okay, let's zoom in on the hardware. We keep saying nodes. The document calls it the Tedford Technologies node, the core operational unit. Sounds complicated.
If we're talking to our 3rd grader, it's a smart brick.
A smart brick.
Physically, yeah. It's a small, incredibly tough little box. You can stick it on a car, bolt it to a building, or, and this is the part that kind of blew my mind, you can literally bury it inside the road.
Inside the asphalt.
Mixed right in. It's meant to be part of the environment, but calling it a brick really sells the intelligence short. The most interesting concept in the manual is something they call the reflex.
I highlighted that. Local risk computation. What is that?
Think about biology. When you touch a hot stove, what happens?
I pull my hand away. Like, immediately. I don't stop to think about it.
Exactly. You don't feel the heat, send a message to your brain, have your brain analyze it, and then send a message back saying, hey, maybe move. Your spinal cord handles it. It's a reflex. It happens in milliseconds.
Because if you waited for the brain, you'd get burned.
The brain's too far away. In technology, the cloud is the brain. It's powerful, but it's distant. The node is the spinal cord. It's what they call edge computing. If a node sees 2 cars are about to collide, it doesn't call a server in another state to ask what to do. It computes the risk right there, instantly.
So it works faster than human thought.
Way faster. And it gives human-first alerting. But here's where the smart brick gets its personality. The source material describes it almost like a skeptic.
Skeptic? How so?
It trusts no single source. It's like a detective who assumes everyone might be lying. It takes in data from its own sensors, from other cars, from GPS, but it cross-validates everything.
Give me an example of that.
Okay, so let's say your car's GPS says you are driving perfectly straight on the highway, but the node's own internal accelerometer feels you sliding sideways on a patch of ice.
The GPS is lagging. It's wrong.
So the node basically ignores the GPS and says, nope, we are crashing. It prioritizes the immediate physical reality over the digital signal from space.
That's a really important distinction.
Yeah.
It's thinking for itself.
And that leads to this idea of a degraded mode. If the power goes out or GPS dies completely, the node uses dead reckoning.
That's an old sailing term, isn't it?
It is. It just means guessing where you are based on where you were a second ago and your speed and direction. So even if the world goes dark, the smart brick keeps working. It counts its own steps.
Okay, so we have the web and we have the smart bricks. Now I want to tackle the hardest part of the stack, the focus of our translation challenge today. The letter to Dr. Eva Miller-Steller.
This is the deep end of the pool, for sure.
It just feels different. The tone shifts from here's our product to here is the proof. Terry Tedford and Mike Matrici are writing to a scientist, and they're tackling this huge physics problem with what they call the gateway concept.
This is crucial. This is how they answer the question, okay, but how does this ground network talk to the rest of the world? The letter gets into transceiver repeater architecture.
Which, yeah, sounds like gibberish to most people. How do we simplify the gateway? Let's go back to the 3rd grade rule.
Let's use a relay race.
Okay, I'm with you. A relay race.
Imagine a huge stadium. The satellite is a fan sitting way, way up in the nosebleed seats. And that fan has a ball. That's the data, the internet signal. And the fan throws the ball down to the field.
Okay.
Now, down on the field, you have a bunch of kids. Some are really tall and some are short. The tall kid is the gateway node. He's the only one who can really see the fan in the stands and catch that ball.
So the gateway is the part that connects to space. It has the fancy radio.
Correct. But the short kids, the embedded nodes, they're buried in the crowd. Or, in the real world, buried in the pavement. They can't see the satellite. They can't catch the ball directly.
So the tall kid passes it to them.
Exactly. The gateway catches the signal from space, then passes it sideways to the buried nodes. And those nodes pass it to the next node, and so on. It's a relay race across the ground.
This answers the big question I had. I was thinking, wait, if the satellite fails, how does this help? But I guess data can just ripple across the ground from a different gateway that can still see a satellite.
Yes. It creates massive redundancy. And the letter explains that on LAN, these short kids, The embedded nodes are literally inside the road. The asphalt itself becomes part of the antenna.
That's the part I found wild. No protruding antennas.
It's invisible infrastructure. You don't have ugly towers everywhere. You drive right over it.
Okay, so the road is smart, but it just looks like a normal road. But this is where the letter gets really specific. The oceanic extension.
Ah, yeah, the water problem. This is where physics gets mean.
The letter states that radio waves, like from your Wi-Fi router or GPS, they die almost instantly in water.
They do. Water is basically a brick wall for those frequencies. So if your goal is a planetary mesh, how do you cover the 70% of the planet that's water?
The letter mentions acoustic communication.
Which brings us to our next third-grade analogy. Whales. Seriously. Think about how whales and dolphins talk. They can't text each other right. They use sound, clicks, whistles, songs. And sound travels incredibly well through water, much better than in air.
So the underwater nodes are singing to each other.
Basically, yeah. The system puts nodes on the seabed on the ocean floor, and then you have surface gateways, which could be a boat or a buoy floating on top.
Okay, I see the chain now. The boat talks to the satellite because it's in the air. Then the boat shouts or sings down to the bottom of the ocean using sound.
Exactly. And the nodes on the bottom pass that message along acoustically to a submarine or a diver or other sensors. It's a completely different language, sound waves instead of radio waves, but it connects to the same network.
And it solves the navigation problem underwater, too. No GPS down there.
Right. So the letter explains they use inertial systems, which is that dead reckoning idea again. The submarine knows how fast it's going and it counts its steps. Then, occasionally, it just pings a surface boat to correct its map. It's like walking in a pitch-black room and occasionally touching a wall to make sure you know where you are.
It's incredible to think about making that seamless. A vehicle just hands off from radio to sound without a hiccup.
That's the vision laid out for Dr. Eva, at least.
So we have the smart bricks, the singing whales, and the tall kids catching signals. But what runs the show? The disclosure framework mentions two big buzzwords, AI and quantum.
Right. The brains and the heartbeat. Let's start with AI. In this system, you should think of the AI as a referee.
A referee?
Or maybe a really, really good traffic cop. The AI is the cognitive layer. It watches the whole game, the whole system, and it looks for anomalies. Is a sensor acting weird? Is a traffic jam about to form?
But it's not just watching, is it? The document implies it takes action.
It does, to keep the flow moving. But, and this is so crucial, I'm glad they highlighted it, the AI is not allowed to silence a safety alarm.
That's the human first principle again.
Yes. If a node's sensors detect a child running into the road, the AI can't say, well, statistically, that's probably a plastic bag, so I'll just mute the alert. No way. The node refuses what it calls false certainty. The AI supports the human. It never replaces the human's right to know about a danger.
I like that. A humble AI. What about the quantum part? That always sounds like science fiction.
You're right to be skeptical. Quantum tech is usually incredibly fragile, like a glass sculpture. But they need it for one very specific thing, timing.
Timing.
To make this mesh work with that centimeter-level accuracy, everyone has to agree on what time it is, down to the nanosecond. If your clock is off by a tiny, tiny fraction of a second, your calculated location could be off by miles.
So the quantum tech is basically a super precise stopwatch.
The world's best stopwatch. And the breakthrough, they claim, is that the mesh itself protects this fragile tech. So it can be used outside a lab, it stabilizes it. So you get that laboratory-grade precision, but out on a muddy road or in a stormy sea.
We've broken down the tech. We've translated the letter to Dr. Eva, but I want to circle back to the why. The so what. Why should anyone listening care about this?
It comes back to that first point we touched on. Equality and resilience.
In planetary benefit.
Exactly. This kind of tech could bring high-tech safety to remote villages, jungles, and contested regions. It means real infrastructure isn't just for wealthy nations anymore. It democratizes safety.
And even for those of us in connected cities, it creates resilience.
Totally. We stop relying on that single light bulb in the sky. If the satellites fail, the ground takes over. If the power grid fails, the nodes keep talking to each other. It's a self-healing world.
There was a note on trust in the disclosure framework I found really interesting. It said the system is designed to reduce harm, not to control people.
And that's a key philosophy. The node is designed to be honest. It admits when it doesn't know something. In a world of deepfakes and AI just making things up, having a piece of infrastructure that can say, I am 80% unsure right now is, well, it's incredibly valuable.
It's refreshing, honestly, a computer that admits it might be wrong.
It's the only way to build real trust in a safety system like this.
So to recap our third grade picture, we're not building a bigger satellite, we're building a global safety blanket.
Right. Made of smart bricks buried in the street that have reflexes like your hand on a hot stove.
And some of those bricks are gateways, the tall kids catching the ball from space.
And under the waves, we have nodes talking like whales to keep the oceans safe.
All of it watched over by an AI referee that puts human safety first.
That is the TL Tedford living ground mesh in a nutshell.
You know, it really changes how you look at a road. We think of infrastructure as just dirt and stone, passive.
And that's the final thought I'd leave you with. We're moving from a world where we drive on the road to a world where we drive with the road. The road itself is becoming an active participant in keeping us safe.
That is a wild thought to end on. Next time you're walking down the street, look down. The future might be buried right under your feet. Thanks for joining us on this deep dive.
My pleasure.
Catch you next time.